There is a saying, what goes up must come down. Let's learn about physics behind this. When the apple is going up, the force and the displacement are directed in opposite directions. What is the work done by gravity on the apple? Work is negative the force F times the height h. The magnitude of the force of gravity is the acceleration of gravity g times the mass m. Therefore, the work is equal to minus mgh. From the work-energy theorem, we know this is equal to the change in kinetic energy. What work do you think gravity does on the apple as it falls back down? Correct. The speed of the ball at a given height is the same when it is rising as when it is falling. Its kinetic energy is the same at the beginning and end of its path. When an object is subjected to some force and has the same kinetic energy when it returns to its starting point as it had when it started, no matter what path it took, that force is conservative. Gravity is a conservative force. Elastic forces, for example those exerted by a spring, are also conservative. Because the force exerted by the spring is conservative, the mass returns to the same position after an oscillation. This block is being pulled at a constant velocity. When the pulling force is removed, the block comes to a halt as a result of the frictional force that acts upon it. The frictional force decreases the kinetic energy. It is not a conservative force. A car's brakes use friction to decrease its speed. For a conservative force, the work done does not depend on the path taken. In the case of a conservative force, we can define potential energy. The change in potential energy is the negative of the work done by the force. For gravity, change in the potential energy can therefore be written as mg delta y, where delta y is the change in height. If we arbitrarily choose u to be 0 at y equals 0, we can write u equals mgy. If we know the force as a function of position, we can compute the potential energy as a function of position. Consider the one-dimensional case with force a function of x. For a small change in position delta x, there is a small change in potential energy equal to minus F delta x. We can determine the potential energy at a given x by integration. The potential energy at x equals 0 is u0. Suppose the potential energy function is known, but the force is not. Then we rearrange the equation above to isolate the force. Take the limit delta x going to 0. The force is equal to minus the derivative of the potential energy. Let's consider a potential energy that varies with x, such as in the equation shown. What is the force as a function of x? We compute the force by taking the derivative, which yields the following result. If we define a constant k equal to 2a, we obtain Hooke's law, the force law for an ideal spring. The potential energy function for a spring is therefore given by 1/2 k times the displacement squared. This feather is subject to a force due to air resistance as well as gravity. Given the definition of a conservative force and how air resistance is affecting the motion of the feather, what kind of force do you think air resistance is? Correct. In general, the net work done on an object can result from multiple forces, some of which are non-conservative. We have in this case, for instance, the friction force F sub Fr, the force F exerted by the donkey, the normal force N, and the force of gravity mg acting on the block. In general, the change in the kinetic energy is equal to the sum of the work done by all the forces acting on it. From the definition of potential energy, the work done by the conservative forces can be obtained from their associated potential energies. The quantities W sub Nc, represent the work done by non-conservative forces. Rearranging, we see that the change in the total potential plus kinetic energy is equal to the work done by the non-conservative forces. We will explore the implications of this in the next section.